In these examples, we are going to see about the analyticity of a complex function. So, at the beginning, we will revisit the definition of analyticity of a function, and also we will have the necessary and sufficient condition for a function to be analytic at a point. Have a look at these definitions. A complex function f of z is said to be analytic at a point z0 if f is differentiable at z0 and every point in some neighborhood of z0. It means a function f of z will be analytic at a point z0 if it is differentiable at that point and it is also differentiable in the neighborhood of that point. A function f is said to be analytic in a domain D if it is analytic at every point in D. A function f that is analytic throughout a domain D is also called holomorphic or regular. A function that is analytic at every point z in the complex plane is said to be an entire function. The necessary condition for analyticity of a function. Suppose f is a complex function and is differentiable at a point z. Then at z, the first order partial derivatives of u and v exist and satisfy the Cauchy-Riemann equations. So in a summary, we can say that if f of z is differentiable at a point z, that is a point xy, then at z, the first order partial derivatives of u and v exist and the Cauchy-Riemann equations will be satisfied. This theorem is known as the sufficient condition for analyticity of a complex function. Please pause the video and read the theorem carefully. This theorem says, suppose f of z equals u plus iv is a complex function. Now if u and v are continuous and have continuous first order partial derivatives in a domain D, and if u and v satisfy the Cauchy-Riemann equations at all points of D, then the complex function f of z is analytic in D. There is a criterion for non-analyticity. It is like that if the Cauchy-Riemann equations are not satisfied at every point z in a domain D, then the function f of z cannot be analytic in D. Example 1 says, show that the function f of z is analytic for all z belongs to C. It means that we have to show that the functions u and v are continuous, all their partial derivatives are continuous, and the Cauchy-Riemann equations are satisfied for all z belongs to C. Here f of z is given as 3z square plus 5z minus 6i. We write x plus iy in the place of z, and then after simplification we get our u function and v function. Now to find all the four partial derivatives, u sub x, u sub y, v sub x and v sub y, and we see that u sub x and v sub y are equal, and also v sub x and negative of u sub y are equals. It means the Cauchy-Riemann equations are satisfied. So the Cauchy-Riemann equations are satisfied and also the partial derivatives are continuous for all z belongs to C. Therefore, f is differentiable for all z belongs to C. Since f is differentiable at all z, which means for every z there must exist a neighborhood in which f is differentiable. So we can say that f is analytic everywhere, which is also called entire function. Example 2. It says that we have to show that the function f of z equals square of absolute value of z is not analytic at any point. At first, we have to simplify our given function. So after simplifying, we got u equals x squared plus y squared and v equals 0. Now we will find all the four partial derivatives for u and v. We got u sub x equals 2x, u sub y equals 2y, and both of the v sub y and v sub x are 0 since v is 0. Now we see that one of the Cauchy-Riemann equation is u sub x equals v sub y. If we replace this value, we got 2x equals 0, which implies x equals 0. And similarly, from the other equation, we get y equals 0. So we see that the Cauchy-Riemann equations are satisfied only at the origin, that is, only when x equals 0 and when y equals 0. It means the origin. And also the partial derivatives are continuous at z equals 0. It means the partial derivatives we got 2x, 2y and 0, these are all continuous at z equals 0. Since z is only differentiable at z equals 0, so z is not differentiable at any other point in the neighborhood of z equals 0. So we can conclude that f is not analytic at any point. Example 3. We have to show that the given function is analytic in an appropriate domain. The function is defined as f of z equals 1 over z for z not equal to 0. At first, we have to simplify our given function. So we write x plus iy in place of z, and then multiplying by the conjugate term of the denominator in both numerator and denominator, and after simplification we get our u and v. Now we have to find all the four partial derivatives. Let us see one of the calculations. The formula we are applying is the division rule for derivative. Since we are differentiating with respect to x, so the derivative of x is 1. And from x square plus y square, we will get 2x. And for y square, it will be 0. Now, similarly, we will get the other derivatives. Here, all the four partial derivatives are continuous at all points except at z equals 0, since the given function is not defined at z equals 0. Now we see from the above partial derivatives that the Cauchy-Riemann equations are satisfied except at z equals 0. So we can conclude that f is analytic in any domain D that does not include the point z equals 0. So we have an exception that although f is not analytic at a point z0, but it can be analytic in the neighborhood of the point z0. Such points are called singular point, or we can say f has a singularity at z0. Example 4. We have to show that the function f of z is not analytic at any point, but it is differentiable on a specific line. From the given function, we got our u and v, and then find all the four partial derivatives. Here, the Cauchy-Riemann equations can only be satisfied if u sub x equals v sub y. So replacing the values of u sub x and v sub y. We get y equals 2x. And the other equation from the Cauchy-Riemann equations, we see that u sub y equals minus of v sub x. Now we see that all the four partial derivatives are continuous at every point, since we got the partial derivatives as 4x, 2y, 1 and -1, which all are continuous at every point. But the Cauchy-Riemann equations are satisfied only for a particular condition, which is y equals 2x, and it represents a line. So we can say that f is differentiable along the line y equals 2x. However, for any point z on this line, there is no neighborhood or open disk about this point z in which f could be differentiable. So we can conclude that f is nowhere analytic but is differentiable along the line y equals 2x.